lights, but I'll check it out.
Let's test it. I was thinking
But if people are talking in the back, so yes, louder than this.
Alright, good morning everybody. Are we all ready to start? Great. So, yesterday we had another fun contest. It turns out that 10 problems are too few. So today there will be more problems again. We'll see what happens. Yeah, okay, so again today we'll start the session with going through the solutions from yesterday with some break in between, and we'll see what happens then. Alright, so let's start with an easy problem, the problem of overlap. So we have given a collection of days. This is just a way to have multiple test cases in one. And within each day, we have a collection of lectures. And it look like this. And the question was whether or not it is possible to find a pair of lectures that don't overlap each other. And who paid attention during the very first lecture I gave here shouldn't have problems with this task, because we know that there is one clear optimal strategy to look for such lectures. If we want a pair of non-overlapping lectures, the first one to choose, we lose nothing if we choose the lecture that ends the earliest between all of the lectures. Because if we have any other pair, we can take the first lecture in the pair and swap it for this one, and it will still be a valid solution because we are only moving this end to the left. So this is a very good candidate for the first lecture, and from symmetry, a very good candidate, actually the best candidate for the second lecture is the lecture that starts the latest. So all we need to do is take the maximum of the beginnings, take the minimum of all the ends, and the minimum of all the endpoints is to the left of the maximum of all beginnings. We have just found a valid solution, and if this is not true, if all of the lectures end only after all of the lectures begin, then clearly there is no solution. So this was the entire thing we needed to do. Find this value and also the index of this lecture so that you can output it, find this value and this index. And if you were successful, if they are in this order, then output that it has a solution. If they don't, output it doesn't. So this was reasonably easy. I think everybody got this one. The second easy problem with almost no idea was the problem where we had to just to rotate the strings, reverse the strings, and manipulate uppercase and lowercase characters. This doesn't have any algorithmic idea, this is just plain annoying. It tests your implementation skills. The best thing you can do in such cases, reuse as much as you can from standard libraries. So, first of all, when you are asked to do rotations and reversals, do not implement them on your own because you may make mistakes. Just use the standard functions, reverse and rotate, that do it for you. When you are supposed to change the cases of the letters, know that there is a function, that there is, for instance, in C++, the library CC type, which is just the plain C library C type .h wrapped into a std namespace. So in C++ you want to include this one, in plain C you used to include this. And this contains all kinds of useful functions to work with letters. There are functions to test whether something is a letter, whether something is a digit, whether it is uppercase, whether it is lowercase. there are functions to convert the letters to uppercase, to lowercase. So you don't have to think about, like, do I check whether it is between 65 and 90, what was it, to see whether it is an uppercase letter, but you just call this. We will not make a mistake with a less than or equal sign and such. So the best thing you could do is when modifying a word, you go through the word one character at a time, you collect whether they are or are not uppercase, then you do the modification of the word, so you rotate it or reverse it, and then you go through your notes, go to the letter of booleans, and explicitly set each of the letters to uppercase or to lowercase, using again these functions from this library. So it's possible to write the entire solution to this problem without necessarily having to know ASCII codes or use plus and minus ones when doing, for example, checking for the center when you are manually reversing the string. So the more you can use the standard libraries, the more you know what's in there, the shorter your solution will be, the fewer errors in such problems will make. Okay, so let's move on to easy problems with an algorithmic part. The next one is the problem by skipping the queue. So we have a bunch of people standing in line, and here at the end is our hero who wants to make his way all the way to the front. But the other people will only swap with him if he pays them enough. So each person has their own price. For this one it can be 10, for example 8, 12, 5, 10 again, 4, or 14, even 1. So this is an example input. And the numbers means that in order to swap with a person, you have to pay them this number times the distance you want them to go backwards. So, for example, if you wanted to swap places with this person, he has to pay them 10 times 1, 2, 3. So this would cost 30. And then when we are here, we can swap with another person. For example, we can swap with this one. And this swap would only cost 5 because we are now moving them only one position backwards. So, what is the optimal solution and how do we compute it? The first observation with such a problem would be that it is solvable using dynamic programming, because if I'm here, I have some options to choose from, and each of these options, if I use it, for example, if I swap with this person, it always brings me to a smaller instance of the same problem. Again, I'm standing somewhere, in front of me is a prefix of the original sequence, and I'm still asking the same question, what is the cheapest way to get to the front? So if this length were small enough, for instance, if these were up to 30,000, we could solve this using dynamic programming, because we'll just, for each position, we'll examine all of the options we have and choose the best one. So for this position, we'll do nothing. Here we will examine one option, 2 options, 3 options, and so on. So this will run in n squared time. You can improve this solution to work for even larger values of n. For instance, by bashing it with some data structures and such. But there is also a much more clever solution that runs in linear time and works greatly. So these two approaches are not mutually exclusive. It's not like the problem is solvable either greedily or by dynamic programming. In this case, there are both types of solutions. You can solve it using DP, but you don't have to. And the idea towards a faster and easier to implement solution is to start from the very beginning of the queue. And to look at it like this. At some point during any solution, we want to travel across this segment. In order to travel across this segment, we have to swap with this person. Sooner or later, we will be forced to swap with them. And this particular unit of travel will definitely cost us 10, because we have no other option. What happens here? At some point during our solution, we want to travel from here to there. And we have two ways of doing so. One of the ways is that this is a part of a longer jump when we are swapping places with this one. But the other way is that we are swapping places with this one. And regardless of where we stand, if we stand here and we swap places with this person, or we stand here, or we stand here, for moving along this segment, we will pay 8. Now what happens here? If you want to travel from here to there, we have to swap places with one of these people. And clearly it's not optimal to swap places with this one because this costs 12. It's much better to swap places with this one already from here because this costs only 8. And now it should be pretty obvious what's going on. As we are going from the right to the left, we can compute the minimal cost we have to pay for traveling across this segment. And the minimal cost is simply the minimum of those numbers that are to the left. So here it will be 5, here it will be 5 again, 5 one more time, and the 1. So we just go from the right to the left. We keep track of the minimum of the costs we have seen so far. And this is always the cost we need to pay, the minimum cost we need to pay for traveling this 1 unit of distance. And as we can see now clearly, if we did it like this, we already know also what the optimal solution looks like. So we start here, we pay 1 to swap to this position. Then for moving any farther, we have to pay at least 5, and the optimal solution is to pay 5 to get here. And now we cannot travel for 5 anymore, so we'll travel for 8 until we get here, and then we travel for 10 until we get here. So the actual optimal solution, if we had to reconstruct it, would be determined by these places where the price changes. So here, there, and to the end. As we only have to produce the cost, you can just do it in the single pass. So it turns out that the answer is simply the sum of all prefix minima of this sequence. Alright, is this clear? Are there any questions? So instead of doing the DP with some data structure, you could just write a single force cycle to solve this problem. Okay, next. Posters. We have a skyline. A skyline is a union of adjacent rectangles. So there's a rectangle like this, a rectangle like that, but we don't care about these boundaries. And our goal is to cover this entire area, this entire shape, using as few rectangular posters as possible. So in this case, one optimal solution would be to have one poster like this, another poster like this, and another one like this, and everything is covered, and the posters are not allowed to overlap. So before we get to the actual solution, this is a type of a problem where you can also see nicely a way of thinking about such problems. As soon as you get to a problem where something is continuous, then there are like infinitely many possibilities how to put on those posters, how to create those rectangles. And we have to come up with an argument to reduce the search space to some finite set of candidates. So we just have to look at rectangles that look like this because this property. In this particular problem, it's pretty obvious that it never pays off to start at a non-integer coordinate. If you already are doing the rectangle, you can always push it to the next integer boundary. So this makes everything finite. But there is still an awful lot of possibilities to check. Like solving this problem by brute force, by trying all possible placements of rectangles, would be really painful, both because the structure of those rectangles is really hard to maintain. Like if you already place this one, and remember that here there is some empty space Or maybe if you are trying placing the second rectangle here, and now having two disjoint areas you still need to cover, it's really hard. So the first thing when looking for a solution is that you want to look for the solution in some kind of systematic way. You want to look, maybe start from the left to the right, or from top to bottom, or try to find some other property that will tell us how to construct a solution, and not to have too many special cases to handle. Another thing that can be done in problems like this one is that sometimes the optimal answer is kind of forced by some property of the problem. And you can see one such necessary condition also in this problem with the posters. And so one example of such a necessary condition are, for example, the top left corners. The only way to cover a top left corner is to have a rectangle, a poster, that has the top left corner in this particular point. So the number of top left corners is most definitely a lower bound of the size of the solution. In this particular case, you cannot have any solution with fewer than 3 posters, because you need a poster with the top left corner here, there, and also there. So this one, that's on the board, has to be optimal. In some cases, for some problems, such a lower bound we will always be able to achieve it. And if we can find such an algorithm, for example, if we can always find a solution that uses exactly as many rectangles as there are top left corners, then we have solved the problem, because we know that there cannot be any better solution, and we have a solution of this size, and that's everything we need. In this particular problem, this is not true. Here is another example of an input, like this. This one only has 2 different top left corners, but sadly we can see that the optimal solution doesn't have a size 2, it has size 3, because the best you can get here is a poster like this, the best you can get there looks like this, and you still have some uncovered area in between, so you need a third poster as well. Okay, so this time the first attempt didn't work, but in general this is a good strategy. Look at the extremities, like the top left corners, bottom corners, whatever. All of the lines that have to be covered. And all of these things will give you some estimates, and they will tell you something about how to construct the optimal solution. And in this case, we have now discovered something else that can also be useful, which is this case. Even after we cover those corners, we still got left with the top side of this rectangle, which remains uncovered. And actually, if you look at these 2 posters, not only are they covering the top left corners of those rectangles, they are also covering the entire top sides of those rectangles. Okay, so this gives us another constraint that however we place those posters, we have to touch all of the tops of the given rectangles. Again, this can give us a lower bound of the solution, but this time it is not completely obvious, because the solution is not always n. Sometimes there can be a single poster that touches multiple tops of those rectangles. So we have an input like this one. And all 3 of these are exactly the same height, then the optimal solution is to have one poster like this. So cover all 3 of these at the same time, and then 2 more posters to cover the rest. So it turns out that this is already the optimal way of solving the problem, because if all of the rectangles have different heights, then clearly the answer has to be n. You cannot have 2 posters with tops at the same level, and you have to cover all of these. So whenever you have an input that looks like this, and all 5 of these are at different heights, then what do you know? You need to have a poster that has its top here, 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 and here. So you need at least n of them. And using exactly n is really easy because we will just cover each of the houses separately. So the only way to get below n, to save some posters, is this way. So you can only save a poster whenever you have two houses of the exact same height, and all of the houses in between them are taller than that, or equally taller. So in this case, even though they are the same height, you cannot cover them with the same poster because there is somebody smaller in between. So this is the only thing we need to check. And the easiest way to do it is by sweeping. So we will go from the left to the right, and we will remember all of the posters like as if they were still going on. So if we have an input like this, when the sweeping line starts here, what we do, we start our first poster at this height. And this poster is going on. Then we get here, and we see that this new building is taller, so we start a new poster here. And we know implicitly that the poster has the top here and the bottom there, because below we have another poster that is still running to the right. And in general, when we already have processed some part of the skyline, we have the sweeping line. The thing we are remembering are the heights of the buildings that haven't been covered by anything lower. So for example, here we had the poster running for a while, but then we got this new building which was lower. So at this point we finished running with this poster and we removed it from the stack. So another way of doing this is that if you were standing here to the right of the sweeping line and we were looking in this direction, which are the sides of the rectangle, you will still see this, and you will still see this inside. So the processing of the next building goes as follows. If it is taller than the maximum of these values, we just start a new poster there, so we push a new value to the stack. And then, on the other hand, if we get a smaller building like this, what happens is, first of all, we pop the stack all of the values that are strictly larger, and then if this exact value is still there, we have this case, so we had a poster, and then we came to this same height, and this means that now we are saving one poster, we are decreasing the answer by one, or it is somewhere in between, in which case this remains on the stack, and then we push this new thing on top of it. So either you get a taller building, you push one thing to the stack. If you get a shorter building, you pop multiple things from the stack, and then you maybe push one more thing to the stack. So in total, this solution is linear in the number of buildings, because the top of each building will be processed exactly once, and exactly once we push it onto the stack, and at most once we pop it from the stack. And that's it. Okay, any questions about this one? No, all clear, hopefully. Or maybe everybody's completely lost and afraid to speak up. That's your problem if that's the case. Don't be afraid to ask questions. There are no stupid questions. At least I don't expect such in this group. Okay, what do we tackle next? Next we can take a look at the problem full, and I will write down definitions from the statement.
Do site não, eu vou do site. Você não tem aí?
Eu cansei de não saber inventar.
O que você colocou?
Mais fácil de trabalhar. Depois eu vou pensar aqui. Eu já vejo.
Okay.
Okay, so what we are given in this problem is a description of a formal system that defines sets. But to make things interesting, the person defining the sets decided that the actual elements of those sets, the atoms, should be the left curly brace or the right curly brace and the comma. So this could be the things that can appear in the set. And as we have no escaping at all in the definition, then everything will become completely messed up because some of the curly braces are actually delimiting the set, some of the commas are actually commas between the elements of a set, and some of them are the atoms, as they are the elements that are stored in those sets. And you can have sets of sets and sets of sets of sets to make things even more complicated. So what we are given is a formal grammar like this. A set is a left curly brace, then a list of elements, and the right curly brace. A list of elements is either the empty word, so empty string, or a list. A list is either a single element or an element, comma, and a list. So a list can produce something like element, comma, element, comma, element, comma, element. And we can iterate this operation as many times as we want, and then we can conclude it by changing the last list to just an element. And each element is either a single atom, so a single of one of these three characters, or again a whole set. So each of these elements can turn to a left curly brace, a list of elements, and a right curly brace, and we can repeat the whole process over and over again. Okay, so this entire thing you have been given is what's called the context-free grammar. You have some symbols here on the left side, those are called non-terminal symbols, and here on the right-hand side we always have a few options. So whenever you see this non-terminal symbol, you can replace it by one of those options. And in this grammar you can generate a bunch of different strings. And the question is to recognize the good strings from the bad strings. So given a string of characters, left and right curly braces, and commas, tell whether it can or cannot be generated by this particular grammar. And now, this is a problem where the knowledge of theory behind these grammars can be really helpful. But essentially, even if you don't know it, it's easy enough to come up with everything you need, as long as you are thinking in the right direction. The wrong direction of thinking is trying to understand the system. So you probably can solve the problem, but it will be painful. You have to analyze what is going on and try to come up with your own different set of rules you will be using for checking whether those strings are good or bad. And in a problem as ugly as this one, you are very likely to forget something. If you go this way, the best thing you can do is to also write a generator. So as soon as you submit your solution for the first time, you get the wrong answer. The first thing you should do is spend a few minutes on writing a very quick program that will use this grammar. In each step, make a random choice and use this program to generate valid strings. Then you can check whether your program actually accepts all those valid strings. You can also use this to do some kind of a breadth-first search on those strings, so that you not only generate all of the valid strings, but then you also know that for some particular length, all of the strings you have generated are valid, and all of the remaining strings are invalid. In this way, you can quite easily create test data for your program. And if you actually try to solve this by hardwiring some patterns and saying that this is how to recognize those good ones from the bad ones, this is very likely what you need. This is a type of solution that is almost impossible to debug on paper, but can be debugged reasonably well by just throwing a bunch of cases on it in an automatic way, and then finding the one that doesn't work, and then handling it somehow, fixing your solution, trying to come up with a better, more precise formula. And as soon as this works on a bunch of random cases up to length 10, it should be good to pass. And this is also, this brings me to a more general point about strategy. It's very difficult in an ICPC contest to decide how much time you should spend on debugging at a computer. And usually the answer is 0, because for most of the problems you can reasonably well debug them on paper. It's not as good as if you have a keyboard, but at the same time you are debugging on paper, somebody else can use the computer to solve another of those tasks. And usually this is the best allocation of your computer time. Usually, but not always. There are cases, and this is one of them, when the best investment is to spend at least a little bit of time actually using the computer to help you debug the solution. And these are hard to recognize, and many teams will never do this. Many teams will default to we only debug on paper because it's 95% correct. So sometimes, very rarely, but sometimes it does pay off to just decide that yes, this is the specific type of problem where I need the computer to debug at least for 5 minutes. Let me write a generator quickly and spend some time on this to fix this solution. Also, this is a more general case that also comes up, and did come up at some of the world finals as well. There are problems that are, for example, about observing a pattern. So sometimes there is, for example, a two-player game that has very obscure, difficult to understand rules, you don't really have an idea what's going on. And on paper you can maybe work out 2 or 3 cases and hopefully you will not make any mistakes. And the best way to solve this problem is to write a computer simulation, write a slow solution that is definitely too slow to pass, but it will allow you, for example, to print a table, like for A equals this and B equals this, who wins the game. And suddenly you can see a pattern. You can see that the only thing that matters is whether A plus B is odd or even. And suddenly you can write a 2-line program, submit it and get accepted. And the huge difference between the ICPC and the individual contests is if in the individual contest you just go one problem at a time, and when you get to this problem, then you go, okay, I don't know what to do with this problem. There is a game, I don't know how the game behaves. Then let me write this quick program that just tries all possibilities, explores the entire game tree, and tells you who wins, and let's look at the small test cases. And if you do this in the individual contest, and there is an easy pattern, then you will observe the pattern, and then you will know how to solve the problem, or you will know how to generalize the pattern to larger instances. But in the ICPC, what happens with problems like this one, they get put to the side. Because on paper, you don't have enough information to solve such a task. And the computer is always being used for something else. The computer is always used for developing the next solution, or debugging, or for testing, or whatever. And then later on, you look at the scoreboard and you see, well, nobody got this problem anyway, so let's put it to the side. And it's definitely way too hard. And I've seen this happen in ICPC contests time and time again. The problem that would be reasonably easy for individuals remains unsolved until maybe the very last hour of the contest, simply because of this. And again, in 95% of cases, or even more, the right strategy is to think about the problems on paper. But there are exceptions. And in a few of those cases, it actually gives you a huge payoff to spend just very few minutes on the computer doing this, writing a program that doesn't solve the task, but that explores the task, that gives you additional information about the task. And in many cases, and for many good teams, this is not a huge time investment, because anyways, you should be experienced with writing very quickly, quick and dirty, brute force solutions. This is a very useful skill to have, also for testing your solutions in individual contests. You need to be able to very quickly, if you have a solution that doesn't work, but you think the idea is correct, write a generator. This can be done in a few lines of code if you know how, write a brute force solution. Again, if the brute force solution is something like trial subsets or trial permutations and output the best one, you can just do it using standard routines, library functions, in a few lines of code, if you know how. And in 2 minutes, you can have a whole framework that generates random test cases, throws them at your solution, compares them to the brute force solution. As soon as it finds a discrepancy, it will alert you. Here is a specific test case you can debug on. The good contestants can do this within 5 minutes of time. And it is a very good skill to have. And an extension of this is precisely this exploratory solving of problems. It doesn't come up often. Let me stress that this is not something that should be part of general everyday strategy. You will maybe use this once every 10 contests if you are doing it right. But still, it's a thing to think about, that you can try to solve a problem also by spending computer time on exploring the problem, finding out how it behaves. For instance, here, whether this just generates a set of all strings. Maybe you don't see on paper, but if you try to compute the program, you will see a pattern in the strings that are generated by this programmer. Maybe yes, maybe not. If you can do it really quickly, maybe it pays off. I mean, even there may be times during your competition when you don't use the computer for anything at all. Sometimes you get stuck, sometimes you are not finished thinking about any of those problems, and maybe this is the right time to spend 5 minutes exploring one of these problems. Alright, but let me get back to this one, and let me get back to an actual solution. So what do we have here is a context-free grammar. The context-free grammar has some non-terminal symbols, so some symbols that represent a state, so we are still rewriting something around here, and some terminal symbols, which are these letters that once you generate a curly brace, it will remain a curly brace forever. So in general, these context-free grammars can have rules or productions of this type, that some non-terminal symbol alpha can be rewritten into any arbitrary string with as many different terminal and non-terminal symbols. So let's use, for example, zeros and ones as the actual terminal symbols. So we can have something like 0, 0, alpha, 1, beta, or we can have 0, gamma, and so on. And now, for these context-free grammars, it turns out to be the case that deciding whether or not you can generate a given string is a decidable problem, and in fact it can be decided in polynomial time. The main problem is if you have rules like this, that you take just one symbol and you replace it by a long string of symbols. It's kind of clunky because if many of these symbols are non-terminals, you don't really have an idea how long a substring will be generated from this one. But, well, let's see what's going on. If you have a grammar like this, you start with some starting symbol. In our case, it was set. So we have a starting symbol, and in each step, you take the symbol and you rewrite it into a string of characters. So this will produce a string, and in this string you can have another non-terminal symbols, and then you rewrite those, and those. But if you have terminal symbols in between, those just get copied in all future generations of the string. So you don't have any way to change the order. You can just take a symbol and replace it by any of those possible right-hand sides. So this form keeps expanding. And at the end, you will get a terminal string. So all of the symbols will be just ones of these, in our case, or zeros and ones. And now if you want to check whether this is a good string, whether it can actually be generated from the sigma, we kind of need to do this entire construction backwards. So if you have, the first rule would be that the sigma can be rewritten into 0, alpha, 1, beta, 1, and there's a 0 here, and there's a 1 here. So far it's looking good. The 0 is this 0, the 1 is this 1, but we don't know which is this one. There can be many of them, and like for each of them, we have to ask the question, what if this is the correct one? Can I generate this starting from alpha And can I generate this starting from beta? And suddenly we are starting to see a pattern going on here. The new question we are asking are again questions of the kind that we have a substring of the output, and we are asking the question whether it can be generated from one of those non-terminal symbols. So in order to solve the question, to answer whether a given string can be generated from this starting non-terminal symbol, we just need to answer all such smaller questions, or a subset of them we actually need. So we can do this using dynamic programming. For each substring of the given string, and for each non-terminal symbol, we'll ask the same question, whether it is possible to generate this substring from this symbol. And once we answer all such questions, then we know the final answer whether this entire string can be generated from this one. The base case is whenever we have a very short string that does actually appear on the right-hand side of the rule. So a string that consists of just a single curly brace can be generated from non-terminal atom. And a string that consists of atom can be generated from element, so the string of a single curly brace can also be generated from element. Now, in general, what you need to do to have so this would be the outline of a working algorithm, but the time complexity can depend on the complexity of these rules. If you had a rule like this, then you would have to try all possibilities when you are asked the question whether this string 0, 0, something, something can be generated from alpha. Then you have to try all possibilities. Where are the boundaries? Like, can I generate this from the first alpha, and this from the second alpha, and this from the beta? Or can I generate this, and the entire rest from alpha, alpha, and beta, and so on? And if at least one of these is true, then you can generate the entire string from an alpha. And if all of these are false, then you cannot. The problem here is the more you have of these non-terminal symbols on the right-hand side, the longer it will take to try all these possibilities. But there is a very easy trick. You can change the grammar into a so-called normal form. This is the normal form invented by Chomsky. And the trick is very easy. We'll introduce new symbols, and you will break apart any long right-hand side. So instead of having this one, you will have alpha goes to 0 and alpha 1. Alpha 1 goes to 0 and alpha 2. Alpha 2 goes to alpha and alpha 3. And alpha 3 goes to alpha and beta. And now, if these are new symbols that are completely unused elsewhere, what you got is whenever you start by using this production, you have to use this one, and then this one, and then this one, so the effect is exactly the same as the original rule. But at the same time, each of these individual rules has a right-hand side of size only 2. And as soon as you do this, then there is only a linear amount of testing. You are looking whether you generate a string from alpha 3 and using this rule. You just need to test a linear number of possibilities. So for each boundary from the left to the right, you ask the question, can I generate this from alpha? Can I generate this from beta? And if the answer is both yes, then you answer yes, I can generate this entire string from alpha 3. So the entire solution, the easiest solution to implement for this problem I'm aware of, is that you take this grammar from the problem statement, manually on your own, you convert it into such a way, such a normal form, you hardwire this into your program, and then you take the input string and you do this dynamic programming. So for all of the substrings, starting from the shortest all the way to the entire string, and for all of the non-terminal symbols in your new grammar, you ask the question, can this substring be generated from this symbol? And you answer it by trying a linear number of possibilities. So the overall time complexity of this solution is n cubed, where n is the length of the string. So we have n squared different subproblems we are solving. When solving a subproblem, we'll be trying all possible ways to split it into two halves. That's why we are trying n possibilities, or on the order of n possibilities. And the n cubed is actually multiplied by the number of the non-terminal symbols in the grammar, but this is a constant. So this is like a formal language theoretic solution to this problem. And actually, what's going on here is called like parsing of a context-free grammar, and this is an important part of, for example, compiler design. Many of the programming languages and like if you look at the syntax of a programming language or the reference of a language, you will see similar grammars defining what are legal expressions, what are how does the body of a function look like, and so on. In order to compile a program in such a programming language, the compiler has to parse your input. So the string you are parsing is the actual text of the program, and you are creating a parse tree like the one I had drawn here. So, and the representation between parts of the string and the norm terminals in the parse tree then tell you this is an identifier, this is a name of function, this is an operator of this type, and so on. So parsing a string for a given grammar is quite an important thing, and a lot of theory is already known behind this. There are specific grammar types that are easier to parse than context-free grammars in general, but at the same time still give you enough expression power. And it's an interesting area, so if you are still deciding what to study, what to focus on, maybe somebody will be interested in looking at this closer. Okay, what's the time? Oh, we still have the time to do some more. Okay, so let's do one more problem and then we'll have a break. So the last problem before the break will be the problem about moving furniture. Okay, so what do we have here? In this problem, we are in a house. We have n pieces of furniture. Each piece has some different weight, or maybe some of the weight may be equal. The problem is that the pieces of furniture are not in their desired spots. There are n places around the house. Each place has a piece of furniture, but we want to swap some of them. So formally we want to make a permutation of those pieces of furniture. And the question is, what is the minimal effort way of doing so? So the only thing we can do, we can swap both pieces of furniture, and the difficulty of this, the price we are paying, is the sum of their weights. So whenever we have to move a piece of furniture and swap with another one, somebody has to carry it, and the amount of energy this requires is proportional to the weight of the piece. Okay, so the first thing we can do with the permutation, obviously we can break it into cycles. Each permutation can be decomposed into disjoint cycles. So right now, we know that inside our house, we have a situation that looks kind of like this. There are 3 pieces that want to be swapped. In the cycle border, there are another 4 pieces, and then maybe a piece or 2 that are on their correct places, and maybe there is a pair of pieces that want to be swapped like this. So this is the situation. To start solving this problem, let's focus just on a single cycle. So maybe the weights can be something like 10, 70, 20, and 40. What is the optimal way of solving this? one observation, if you forget about the weights completely, one observation you can make is in order to sort a cycle of length k, you need to make at least k minus 1 swaps. Why is it the case? Because as long you can only place one element in its proper place in each swap, and only at the end when you have two elements left you can place both of them to the desired places in the same swap. So the first observation is at least k minus 1 swaps. The second observation, we have to move each of the items at least once. In particular, we need to move this item at least once, and this item at least once, and this item at least once. So for each of the swaps, we are moving two of the items, and we are paying the price of one we move and the price of the other we move. And we know that among those prices we will be paying, at least once we have to pay 70, at least once we have to pay 20, at least once we have to pay 40. So for this particular cycle, we know that there will be at least 3 swaps. Each time we are paying at least 2 of the costs, and somewhere there is a 70, somewhere there is a 40, somewhere there is a 20. And clearly the best solution we can now get is we fill all of the remaining numbers with the weight of the smallest item. 10, 10, and a 10. So there is nothing better than this. And we can always have a solution that has exactly this cost. So what we just shown is that the cost is greater than or equal than k minus 1 times minimum of the weights plus the sum of other weights. And this is always possible, because what you do is, well, the 40 wants to go here, this is the cheaper, this is the lightest item, so we swap these two, we are paying 40 plus 10, then we swap these two, paying 20 plus 10, and then we swap these two, paying 70 plus 10. So this is clearly the optimal solution. You need to have at least k minus 1 swaps, you need to have at least this cost, because you need to move each of the heavier items at least once. So this is clearly the optimal solution, and you can always make it. So this would be the entire problem, right? We just break the permutation into cycles, solve each cycle separately, and we have the answer. And this is where mistakes are made on this problem. You get this far, you implement this solution, and then you get a wrong answer, and you start and think, what just happened? And the thing that just happened is that when we are proving this about the single cycle, the assumption was that the single cycle is the only thing there is, that there are no external elements. And it may be the case that sometimes it is not optimal to solve each cycle separately. For instance, if these costs, if these weights were much higher, just to be on the safe side, and somewhere else in the house, we have a very, very light item, based on 1. Here's another thing you can do. Instead of moving each of these items once, and then using this item to move it 3 times, maybe it's a better solution to enlarge the cycle by bringing in a very cheap item. So we'll begin by swapping the 1000 with the 1. Now we can do the previous solution. So we move each of these exactly once, and you will get the 1 at some other location. All 3 of these will be on their desired places. And then at the end, you swap the 1 back with the cheapest item on the cycle. So in this way, you can get a better solution in some cases. In this case, you will get a better solution because you are not moving the item weight 1,003 times around the circle. You're just moving it once away from the circle and once back. So we save approximately 1,000 by doing so. And again, once you make this observation that I can bring in an external item sometimes, then the problem is easy because it's obvious what to do. The optimal solution of the second kind has to have the following form. You take the cheapest item, the lightest item on the cycle. You take the lightest item overall, and those two will be the two you swap because doing anything else will only increase the cost. So you move the lightest item out of the circle, you replace it with the lightest item overall, you do the entire circle back, and then you swap it again. In this way, the cost of the solution is twice times the minimum of the cycle plus the sum of the others plus twice the minimum globally, well, globally outside of this particular cycle, but if the overall minimum, overall smallest element is already on the cycle, then it pays off to swap it out of the way. So you can just take the global minimum and be sure you don't mess up anything. So this is the entire solution for the furniture problem. To summarize, take the permutation, break it into cycles, solve each cycle separately, but also for each cycle, consider the second option. Instead of solving the cycle on its own, it may be better to bring in the lightest of all items and use that as a, like, almost as if it were an empty space, because this is exactly what we are doing. We move one of the heavy items out of the way, we have as if an empty space, we shift everything, and then we bring the item back into the empty space instead. But as we don't have any actual empty spaces, we are using the lightest of the remaining items as the as if empty space. Okay, so that's it for problem furniture, and now we will have a 10-minute break.
Hi.
E aí, cara?
Você vai querer comer agora?
Não. Então, como você se sente agora sendo usuário de mais silêncio?
Sim.
Those are the last problems. that is not much better to try to repackage this now.
This one too. Like, as you had so many problems to like
if you already get to this situation, there is not much more. Sometimes it happens that you will go into this contest with almost finished problems. And if you are already in this situation, there are no good choices. You will have to pick whatever seems most likely to work. The good thing you should learn from this is the lesson from the future. Try more to avoid before starting for this, which will find it great. It may be important to this. Back when I see sometimes if somebody is still using a computer, you already have a solution to the problem, so you can access. Starting from it. Sometimes what is needed is when you start writing down an outline of your role, and you say, I'm missing something, you realize I'm going to next to the structure because I just need this table, so the reverse data index. This will help you fill in details and this will help you make fewer mistakes as you actually slowing down, being more careful, good strategy for pleasure.
Cada um faz uma vez, os três
Faz aí. X igual a 10 a 30 vezes 10. Não, sem dúvida.
Acho que da ordem 100 vezes igual.
Mas o número constante talvez deu, mas com duas variáveis mistas. Agora bota int.
Aqui?
Não, tipo, bota int y igual a 10 a quinta e você faz.
É constant expression, ele vai pegar.
Eu sei, a gente
Mas é constant expression, ele vai pegar isso. Aliás, talvez se eu fizer isso aqui.
Ah não, mas aí você roubou. Não, isso não é caralho.
Legal.
Agora eu vou pegar o número alto. Não.
só
Visual exagero. A new variable C.
Ah, tá bom. Devia fazer, pô. Ah, não devia não.
Não dá pra saber.
Não, é verdade, se ele avisasse, ia ser tipo, em toda a multiplicação desse, ele ia falar. Não, você pode estourar, cara.
Você tá assignando tipo uma multiplicação de números.
Ah, bom, mas seria meio chato.
Ah, eu acho que tem W-type, não tem? Acho que tem uma play que faz
Você
isso.
fala em large. Não, eu acho que ele só me deixa em large. Mas é assim, de sair uma compulsa. Deve ter uma opção.
Vocês estão usando o sistema.
E também, tem uns caras.
Vou fazer uma dança. Ah, tá.
Mano, eu tenho que fechar o da cara.
Não, é só o segundo andar. O segundo andar cabe 50 pessoas, tipo coisa. Mas eu acho razoável, ali fora cabe umas 20, ali dentro cabe umas 20 horas.
O Ian vai ficar vermelho.
E esse fica vermelho, velho.
Se o round que foi a perder, não fosse perder.
Ele ia pular o amarelo.
Cara, no próximo intervalo eu vou colocar um vídeo da capivara.
Oi?
Melancia. Tem um vídeo de uma capivara comendo melancia que dura 20 minutos.
E você tá falando isso pra câmera pra fazer o show do intervalo?
Vou baixar o vídeo.
Vamos lá. Cara, é muito bom ter um computador aqui. Já. Agora você não sabe que a gente vai fazer. Será que eu
Let's go. We still have, I think, 4 problems left from yesterday. So let's move to the next one. The next problem, talk about will be the problem about the European Union statistics, which is essentially just a thin story cover for a 2-dimensional query problem. So what we are given is a collection of points, or maybe it may be slightly better for us to visualize them as unit cells in some space in the 2-dimensional plane, like this. And then we are given a bunch of rectangle queries, and for each rectangle query we have to count the number of items that fall inside this particular rectangle. And we have to do it in an online fashion, so we have to answer one query before getting to the next one. So we cannot pre-process anything useful. In particular, we cannot pre-process all of the queries at the same time. If you get all the queries at once, there may be easier solutions based on sweeping and such. But if you get the queries one at a time, then you have to do something slightly more clever. As I've seen from your solutions, for the teams that did solve this, the weapon of choice seemed to be almost always, if not always, back short tree. So I will be talking about something slightly different now. I will show you another solution, another data structure that can be used to answer these 2-dimensional queries, and that can sometimes also be used in other contexts as a truly online data structure. The main concept we will talk about now will be persistency, which means remembering your past states. So a persistent data structure is a data structure where you not only have the current state of the data structure, but you can go back in time and look at the contents of the data structure at any previous point. We'll see one simple example how this can be implemented, and then we'll talk about how it can be used. The data structure we will use for this solution will be an interval tree, and this is the unlucky competitive programming data structure. It doesn't really have a real name, because there are also other data structures also called interval tree. Some people call it a segment tree, and there are also other data structures called segment tree that store segments and look differently. Probably the best name for this data structure I've heard, I think, was invented by the Croatian competitive programmers, and the name is tournament tree, because this is actually like the elimination tournament graph. So, anyways, you probably know the data structure. It looks like this. It is a complete binary tree, and we can use it as a poor man's balanced tree to do anything, as long as the range of coordinates isn't that large. So, some basic uses of this data structure are, if you have an array of values, and then you want to do some modifications of the array, either of individual places in the array or of the entire intervals. And also you may want to make queries, which can be point queries and which can be interval queries. Then the interval tree is a good data structure. One simple example is that the leaves can correspond to the individual items in the array, and each internal node can contain the sum of the values in those two leaves, in those two children of the node. And then you can use such a tree to answer queries about the sum of any interval in logarithmic time. And certainly you have seen this and you know many different tricks that can be done with this data structure. One of the traditional tricks how to use this data structure is that you don't actually need to implement any trees. You just need to store this entire thing in an array in the same way in which you can store, for example, a binary heap. So this will be at index 0, this will be indices 1 and 2, 3, 4, 5, 6, and so on. And given the index of the node, you can compute the indices of its children, the index of its parent, and you can traverse the tree without explicitly having to store those links. This will now be a luxury you cannot afford. So in our new implementation of this data structure, we will actually use pointers. You can still do everything in an array without actual pointers, just by remembering indices. But the thing that will matter is that each of these nodes of the tree will have to explicitly store the indices of its children. At the beginning, we can create this tree as a normal static structure. So we will just take an array of nodes, and at the beginning of the array there will be this node at index 0, and it will remember that my value is this, and my children have indices 1 and 2, and so on. So I will draw arrows into the picture to illustrate that this is happening. Now we can still implement any of these standard algorithms to run in logarithmic time. If you want to access, the only difference is that previously, if you have just a static copy of this tree that never changes, you can access the leaf nodes in constant time because you just know the index, so you go there. If you have this version, so there are pointers and each node can point you to its children. If you want to access a particular leaf node, you have to do it in logarithmic time. You start at the root and go downwards. So this is a slight complication, but it shouldn't matter for most of the algorithms. So the implementation of algorithms stays the same. Now let's take a look at what changes if we make an update to such a tree. And again, let's keep it very simple. Let's just do a point update. So we change some value here in the tree, here in the array. What would happen is that this change would propagate upwards in the tree, and it would change some of those nodes. And maybe some of them it won't. Like, for example, if this were a tree where each inner node stores the maximum of its children, then if you increase this value, then these values might change, and this value is still the same, because this one is larger than this one. Anyways, the way to implement this change is to start at the root, descend to the leaf you want to change, make the change, and then on your way upwards, update all of these nodes. You can recompute each of them, and you can store the new value in the node. And this is the important observation here. Making a single update to an interval tree only changes log n nodes. So if this is n, then we can initialize the entire tree in linear time, and then each subsequent update will require logarithmic time. So there will be log n time spent, and there will be at most log n of these cells that change value. And now comes the main and only trick of the entire update, of the entire change we are going to make with this data structure. Whenever we are updating a node, we will not do the same thing we did previously, which is rewrite the value in the node. Whenever we want to update a node, we will create a new node in memory. So I will now draw squares to illustrate this. So if we wanted to make a local update here, we recursively descend it downwards, and now we will make a new copy of this node, and as we go back, we will make a new copy of this node, a new copy of this node, a new copy of this node as well. And what happens there? The old values remain stored in these old nodes. The new values get stored into these new nodes. Even if this one doesn't change, we still create a new node, and we copy the value. And these new nodes will have different pointers to children. This one at the bottom doesn't have any children. These ones point like this. And the other pointer to the other side that didn't change is simply copied. So this entire situation looks like this. So whenever you go out from the branch, you set this pointer to this child, and the other one is copied from your previous version. So what did you get now? The asymptotic time complexity didn't change. You still started at the root, spent log n time going downwards, and spent log n time going upwards. But now, what you have in memory are both copies of the tree. If you start at the old root and go downwards, you see the old version of the tree. And all of the values are as they were at the beginning. If you start with the new root and you go down the tree, you see the new tree. The old values, the values that didn't change, are the same as before. If you go here, you will see the same thing as in this version of the tree. But if you go here, you will see the new updated value. So the only difference is that we now spend log n extra memory cells, and we have both copies of the tree. And we can continue doing so through the next updates. So if there are few updates, time, memory, n plus q times log n. So each extra update just will cost you only log n time, and the difference between this solution and the original non-persistent version of the tree is that this also consumes memory. So instead of discarding the old values, you just create new nodes with the new values, and you read out the pointers in such a way that you get all of the copies of the tree. So the last important thing when doing the implementation is you want to explicitly store the indices of the individual roots. So you know that at time 0, the root is this vertex, at time 1, the root is this vertex, and so on. After each update, you take a new, when you create a new root, you take its index and push it into a separate array. In this way, you can now access each of the historical copies of the tree. You can just start at its root, and then you see what was in the tree at that point in time. Okay, so we get a bit of extra memory, we get the exact same time complexity, and the benefit we get from this is persistency. So we know not just the final state of the tree, but we can recall, look back at all of the previous states of the tree. So far so good? Do we understand how it works? Any questions? Now, the thing to realize here is that this can also be used not just to look back into memory, this can also be used to branch away. So, for instance, this would be a useful data structure if you could have also receive commands undo the last change, and now do something different. Now undo what you did there, redo the previous change, and do something different from there. We can still go back in time, we can still remember this entire structure and do those changes. Have different copies, we can go 2 steps back into the past and then modify this tree, introduce a new change into that tree. So this can be used as a truly persistent data structure. We can go back and forth in time and look at all of those different versions. And now I will show you one tricky way of using this to answer those specific user queries. And the trick will be very easy. So imagine that you are starting, when you start here, and you have an array. Initially, all zeros. And the content of the array tells you, for each row, for each cell, how many different cells have I already encountered. Now the only thing you will be doing is you go from the left to the right, you are sweeping through the entire picture, and whenever you encounter a black cell, one of the given points, you increment the value in the array. Now at any moment, if you were to stop, like here, or maybe let's stop here. So at this moment, when you finish processing up to now, then in each row of the array, you have the number of black cells. So for example, this one isn't processed yet. So in this row, you would have a 1, in this row, you would have a 2, and so on. And now, at this point, we can make an interval query. We can ask the array, what is the sum in this range? And if we ask for the sum in this range, or you take another black pixel here. If we ask for the sum in this range, we get the number of black pixels in this entire rectangle, from the beginning until this boundary. So the total number of black pixels can be computed by the answer for this query at this point in time and this point in time. And this is exactly where persistency comes into play. What we will do is we will not have just a single array, but we will build a persistent interval tree on top of this array. So at the beginning, we have the state that the array was for zeros, then we have the state here, the state there, and so on. And in n log n time, we process all of the endpoints, and we know the state after processing each of them. And now whenever we get a rectangle query, we can look at those 2 specific points in time. We can go back to this time and ask the interval tree what was the sum of this range. And we can go back to this time, ask the interval tree what was the sum of the same range. And this answer minus this answer are these pixels minus these pixels, which are these pixels. So each of the queries can be answered in logarithmic time. You just go to 2 different interval trees you have stored in memory and ask each of them what is the sum of this particular range. In terms of complexity of implementation, this should be roughly as hard as to implement as those nature trees you have in your solutions. But it's a different tool. It can be used in different ways. And in particular, there can be other online problems that can be solved using this only. Okay, that's it for the 2D range queries. Any questions here? Everybody happy? Okay, next problem, navigators. Navigators is a shortest path problem. We are in the plane, we have the locations, and we want to travel from A to B using the shortest path. The only problem is that the graph is complete, which is too large for us to process, and the distance metric is kind of weird. If you are traveling from here to there, we can visualize it like this. And the actual distance we are using is the minimum of these two distances. So distance between x1, y1 and x2, y2 is defined to be the minimum of x1 minus x2 and y1 minus y2. So this is the formal definition of the distance. And given such a distance and a collection of endpoints, we need to find the shortest path from A to B. So the thing we would like to do would be to run Dijkstra's algorithm to find the shortest path. The problem here is the graph is too large. There are too many possibilities, and we cannot afford to explore all of them. So a good way towards the solution seems to be to think about somehow reducing the size of the graph. And we can actually do this, and the way to do so is very simple. So imagine that you are in some point A. And right now you are going to decide whether you will sail to one of the remaining n minus 1 points. But the actual decision you are taking is you are choosing one of the 4 directions you will be sailing. So if we have those 2 navigators from the problem statement, the first one, Bob, is the one who matters, and he will choose whether to sail north, south, east, or west. And suppose that here is some point B, and Bob has the option to, so Bob decides to sail north and go to B. If we were to go there directly, then he would navigate for this long, and then his body will navigate for the rest of the journey. And now comes the important observation. Suppose that there is a point C, which is vertically somewhere between A and B. What happens now? Here's the first example, so this will be C1. One possibility Bob always has is to stop at C1 on the way to B. One thing that can happen looks like this. So they will go here, and then there, and then they will go here, and then there. In this case, the total length for Bob is exactly the same. So he always has the choice of stopping at C1 or any other point which is vertically in between A and B. And if he always chooses to sail north, then he will pay exactly the same amount as he would if he went directly. But sometimes it may be the case, here's an example point C2, that Bob has also a better option. He will sail north until here, he will let Tommy navigate there, and suddenly, instead of sailing these 2, he can just do this one, and let Tommy do the rest. So the thing we have just shown is that whenever you want to go from A to B by sailing north, and there is another point C in between, you can always stop at C. Either you will get a solution of the same value, or you will improve it, but it will never be worse if you make your decisions optimally. So the option of starting at A, sailing northwards, and going directly to B is an option we don't even have to consider. If you decide that I start at A and I'm going to sail northwards, then it is clearly always optimal to stop as soon as you can. So find the first point in the northwards direction and stop there. Because for any other point B, we can make this argument. There's another point in between, and we lose nothing by stopping there first. And if there's another point between A and this C, we lose nothing by stopping there first, and so on. And this gives us the desired reduction in the number of edges. So if you start at A, you only have to consider 4 options. If I'm at A, I can go north, south, east, or west. And each time, clearly I'm losing nothing if I'm going to the closest point in this direction. So if I'm going from A to the north, then I'm looking for the point which is closest in terms of the y coordinate. If I'm going to the south, I'm going to the closest one with the smaller y coordinate, and so on. There may be an issue with ties. So what happens if there are multiple points at the same y coordinate or the same x coordinate? And the easiest answer is we just have to impose one particular order upon those. So in order to actually implement the solution, the easiest implementation looks as follows. You take all of the points given in the input, and you sort them according to primarily x and then y. And in this sorted order, you add edges between the neighbors. So for each point, you go to the closest point with the smaller x and the closest point with the larger x. And if there is a tie, then you just order them arbitrarily and create a chain of those points. And then you independently do the same thing, but sorting first according to y and then according to x. In this way, you will get exactly 4 edges for each point, except for some of the very boundaries which will have to learn. So each point will have at most 4 edges, each going in one line as if in one of these 4 directions. And suddenly you have a graph with n vertices and not n squared edges, but only 4 n edges. And then you can run Dijkstra's algorithm and find the optimal solution. So the main big picture lesson from this problem is draw pictures and play around. If you get a new unknown definition, you have to play around with it, you have to examine its properties, and if this is something you discover, then on my way from A to B, I can always stop by and points lie in between, then suddenly you can use this to your advantage. Alright. The usual question, did this make sense? Do you have any questions, comments? Everybody's happy? Can we move on? Alright, so 2 problems left. Problem n-1 is the problem called Svetopulk, which is an old duke from the history of Slovakia, and the story about his sons is one of our popular folk tales, and like the lesson for young children about the importance of unity, and it has been twisted beyond recognition when writing the problem statement. So the actual problem we are solving is we are given n, and our goal is to decompose it into 3 positive integers a, b, c, such that the bitwise n, a, and b, and c is maximized. Now, this seems to be a problem that should be solvable easily, and to some extent it actually is. Because, like, if n is divisible by 3, it seems to be a good strategy to just split it into 3 halves, 3 thirds that are equal, and then their bitwise n should be the answer, right? Well, yeah, because n, b, and c is less than or equal than the minimum of A, B, and C, because if you take the minimum and then you apply bitwise n with the other 2, you will never increase it, you can only decrease it. And this minimum is less than or equal to n divided by 3. So whenever we can have equality here and there, we really have the optimal solution. So we already solved some of the cases, it's great. Can we do the rest? it turns out that the rest can be a bit more complicated. I will show you two different approaches to a complete solution. One of them will resemble an approach we already used in the problem twice, and the other will be, again, slightly different, slightly new. So what's the first approach? The first approach is to actually try doing the greedy solution. So we are trying to construct the numbers A, B, and C from the left to the right, from the most significant digit to the least significant digits. Now the easy situation is if we can afford to have ones here. So if the leftmost column we are trying corresponds to the digit 2 to the k, and we have n greater or equal than 3 times 2 to the k, then clearly the optimal solution is to put ones into this column. The problematic situation is if we don't have enough. So the current value of n happens to be less than 3 times this particular power of 2. What to do then? Well, the thing we would desire the most would be to just put zeros here and to reserve all of the value for the remaining digits so that we can have at most as many one columns here as possible. But this may not necessarily be possible. Why is this the case? Well, because if n is very close to being 3 times this power of 2, and if you have 3 zeros here, then even if you fill the entire rest of those numbers with ones, you'll still have a plus b plus c less than n. So sometimes we are forced to spend some of the power of n on giving here a useless one, or maybe even 2 useless ones, just to make sure that the rest can still be filled. And this is the actual complete greedy solution. So we are going from the left to the right, and for each column, in order of preference, we would like to see 3 ones, 3 zeros, 0, 0, 1, or 0, 1, 1. And the option we pick is the first option we can pick. And the way to verify whether or not we can choose an option is, like if I give zeros here, then this is precisely the test I need to do. The smallest sum, a plus b plus c, I can obtain is if I fill everything in zeros, and this is clearly less than the current n, or equal, which is okay. And the largest sum I can get is I fill everything in ones. And if this is, let's say this is now 2 to the k, then the sum of these ones would be 2 to the k minus 1, and this times 3 is the maximum I can get by filling everything here with ones. And in this column, if I put all zeros, is this enough to exceed to reach the current value of n? If not, I have to have a 1 or maybe another 1 here, and the value of n is decreased appropriately. So I hope I go from the left to the right whenever I can fill an entire column with ones, which means having the 1 in the result, I do so. And whenever I cannot, I find the smallest number of ones I have to place there, I do so, and I continue on. And each time I place some ones, I decrease the remaining value of n that I'm using for the next columns. Okay. Is everybody happy with the solution? If so, then let's take a look at the other side. Another approach that can also be used to find a working solution. And we'll start from the opposite end. This time we won't be greedy. This time we won't be choosing one option only. This time we are aiming for a solution that tries all possibilities. In some sense, all possibilities. So we'll be trying some different ways to assemble the A, B, and C, and we will be sure that the optimal way is among them. So, what do? We start by looking at the least significant digits. In general, there are 8 combinations that can be there, because each of these bits can be either 0 or 1. We can eliminate 4 of these because we know the parity of n. So, for example, if n is odd, then there cannot be 0, 0, 0 because the sum of ABC would be even. If n is odd, there must be an odd number of 1s. If n is even, there must be an even number of 1s. Additionally, the order of these digits doesn't matter. If you use 1, 0, 0, it's the same thing as if you use 0, 0, 1, because it's the same solution. And even if then later on you assign the bits differently, you can always rearrange the bits within each column to get another valid solution. If you rearrange these bits, the sum of A, B, and C doesn't change, and the bitwise end of A, B, and C also doesn't change. So it turns out that we only need to consider 2 options in either case. If n is even, we need to consider 0, 0, 0 and 0, 1, 1. And if n is odd, we need to consider 0, 0, 1 and 1, 1, 1. So in either case, there are only 2 options. And now what we can do is each of them brings us to a smaller state. So we had n equals a plus b plus c. Let's assume that we chose this option. So now we know that this is a prime 0 plus b prime 1 plus c prime 1 for some numbers a prime, b prime, c prime. And this is appending the next digit. So now we know that n minus 2 divided by 2 equals a prime plus b prime plus c prime. Right? So we just subtracted 1 here, subtracted 1 there to get zeros, and then we divided everything by 2. So the original question, given n, what is the maximum bitwise n I can get, is either I use this, and then I take the optimal solution for n half, and I place it here, or I use this as the last column, and then I take the optimal solution for n half, n minus 2 divided by 2, and I place it here. These are the only 2 options for the optimal solution. The optimal solution for n is either the optimal solution plus for n half plus this column, or the optimal solution for this plus this column. And now we continue doing the same thing recursively. So for the optimal solution of n half, we will go to optimal solution for n divided by 4, n divided by 8, n divided by 16, and so on. So at each of these levels, we will be solving a bunch of recursive calls. Now alone, if we do this just like I described, this solution will still time out. Why is this the case? Well, because we have like 60-digit numbers, and at each digit I'm trying 2 possibilities. So I'm making 2 recursive calls, and the time complexity would be due to the 60. The thing to realize here is that as we are going closer to the end, all of the subproblems we are solving will be small because we are halving the value of n in each iteration, roughly halving. Either we go to the half or we go to the half minus 1. So the actual values, even if we start with 2 to the 60, we will go to 2 to the 59 and 2 to the 59 minus 1. And from here we will go to the 2 to the 58 and 2 to the 58 minus 1. And from here we'll go to 2 to the 58 minus 1 and 2 to the 58 minus 2. We already see what's happening is that here we are solving the same subproblem twice. And as we go on, then at each power of 2 we will be only interested in very few of the problems. And as we are going downwards, then from some point on, yes, there will be a lot of small problems, but they are all small. So the actual number of subproblems we need to solve is only roughly proportional to log n squared. Now, because here's 1, there's 2, there's 3, there's 4 of them, and the depth of this tree is roughly logarithmic in n. So in our case, if there are 60 digits, there will be roughly several thousands of these subproblems only we need to solve. So if you do this recursive solution that tries all possibilities and applies memoization, then you will have a working solution that is also very fast, and you can be sure that you then didn't miss anything. So not just the greedy approach from the front, but also a kind of a brute force, examine all possibilities approach from the back can be made to work. And this observation is quite interesting, that the number of problems you will need to solve is kind of small. Yep.
I don't understand how we guarantee that we are maintaining that the sum of a plus b plus c is equal to n in the second solution.
So the guarantee is here that if you choose the last bits to be all zeros, then the values you fill in here must sum exactly to n half. Because if you append those zeros, you multiply a by 2, multiply b by 2, and multiply c by 2. So whatever was the sum of this, if you append those zeros, you will get twice the sum. So in order to construct the optimal solution that ends in 0, 0, 0, you construct the optimal solution for exactly the sum n divided by 2, and then you append those zeros. And this is how it is preserved. And again, if you choose 0, 1, 1, then you know that the rest you should fill in here is the optimal solution for exactly this value. Because then, if you take this value, if you append all zeros, you will get the value n minus 2, and if you change this to zeros into ones, you will get the value exactly n.
Okay.
So whenever you choose the last digits, you know the sum of the remainders of the numbers.
All right.
And we are left with just one problem from the problem we said yesterday. And this is my favorite problem. This is a problem about the minefield. We have a collection of mines. Each mine has a location, a length, and a radius. And whenever you trigger a mine and it blows up, then it triggers all of the other mines within the radius. Then those blow up, and this spreads to the right, to the left, until it stops somewhere. The goal in this problem for each mine, compute the number of mines that will explode if you trigger just a single one at the start. And this seems to be an easy problem because it's very simple, it's just on a line, there are just some integers as the input. Then you start thinking about the structure, you start thinking about some kinds of maybe connected components, strongly connected components. If I trigger this one, it will explode that one, and this will be the same, but then locally there could be some small ones with some properties and whatever doesn't really work. And it starts to seem really painful. There's one thing we can certainly do with this problem, which is kind of like incrementally converge towards solution. So at the beginning, we have a configuration of mines, and each of those has a radius, so it has an interval which triggers. And one thing we can realize is that if we number the mines, 0 through n minus 1 from the left to the right, so this is the order in which they are given in the input, then the final state is such that each mine has to explode the contiguous interval of those mines. It's not possible to explode the mine here, explode the mine here, but leave this mine unexploded. Because anything that triggers from one side to the other have to take everything in between as well. So for each of the mines, we only have to find two values. What is the index of the leftmost mine that will also be triggered, and what is the index of the rightmost mine that will also be triggered. At the beginning, if we are just given the input, we can initialize these values by simply doing binary search. So for each of the mines, if we know its radius, we can compute this coordinate and use binary search to find the leftmost mine that is still in the interval. And we can compute this coordinate and we can find the rightmost mine that is still in the interval. Sometimes, like for a mine like this, it will happen that the leftmost and the rightmost, or the rightmost or maybe both, will be the mine itself. So these are the initial values. So we have now two arrays, an array L and an array R. And for each mine I, we remember the leftmost mine and the rightmost mine that will also explode. And now this information can be updated because suppose you have a mine and you already know that everything in the interval, so this is mine I, and everything in the interval from Li to Ri will explode. But this interval can also contain some other mine with a much larger radius. It will also then trigger yet other mines. So if we already know this interval, what we can do is we can take a look at all of the mines in this interval, and for each of them, take a look at their value, Lj and Rj. And we can take the minimum of all Lj, so if you have a mine here that already has a range up to that point, and another mine here that already has a range up to that point, this is the best one we take. So we can take a look at this interval, take the minimum of all Lj within the interval, take the maximum of our R, so another mine can be here, and this one can be maybe slightly better than that one. So this would be the minimum of all L, this would be maximum of all R. And we now know that this mine will explode not just everything in this interval, but everything in this interval. So this process I will call an update of a single mine. An update of a single mine means you look at all of these values within the interval, then you take the minimum of L's, maximum of R's, and you update these two values. There is a very easy way to do these updates efficiently, which is you take these two arrays, each of them separately, and you build an interval tree on top of the array. So now you can do each of these queries, interval query to find the minimum on the L, interval query to find the maximum on the R in logarithmic time. There's one technical thing you need to do. Not necessarily. Okay, so far we got here. We can look at a single line. We can update it in logarithmic time. And that's it. That's the tool we have. Now, we could do a solution to this problem that would look as follows. In an infinite cycle, go through the mines and update each of them. What happens is that either we will find a mine that actually updates, so the range of this mine increases, you learn something new, or we get to an iteration where nothing new happened. As soon as this happens, and as soon as we get an iteration where each mine is happy, then we have already computed the final state. There cannot be anything else, there cannot be any situation where a mine explodes another mine and we don't know about it, because if we look at this particular mine, then we would see an option to increase one of these ranges. So as soon as the solution converges, we have the optimal solution computed. For each mine, we have this actual interval. Is this clear? So now the only question is how long the solution can take to converge. And the answer is too long. Well, it can be shown very easily that the solution has to be polynomial. Because in each iteration through all the mines, either we shift one of the boundaries, and this can happen only polynomially many times because we are going closer to the end of the array in either direction, or we don't change anything and we are done. So we have a polynomial time solution, but it's not fast enough. If you just implement it in a way that you go through the lines from the left to the right, each iteration, there are inputs that will cause you n such iterations until the entire process converges. A very simple example will be minds that trigger themselves from the right to the left. At the beginning you know nothing. In the first pass you will learn only about the beat at the end. In the second pass you will learn one step more. And in 10 passes. So this means the worst case time complexity would be n squared time log n for this solution. Now there are also other approaches that work for this problem, processing the minds in some specific order and thinking about it some more. But there is a really easy implementation that solves this problem, and there is quite an involved argument why it does so. And this is my preferred solution, so I'll show this one. The only things you need to implement are these two interval trees. So you have to be able to do the minimum queries on L and the maximum queries on R. And as soon as you have this, as soon as you can do an update of a mind in logarithmic time, you can get an n log n time solution that looks as follows. In an infinite cycle, go through all the minds from the left to the right, and then go through all the minds from the right to the left. And after a finite number of iterations of this process, the process has to converge. So as soon as you see an iteration where you make no changes, you can stop and output the answer. And so in the previous solution, we just considered that we do it in some arbitrary order, and then that can be back. But if you do it in this specific order, back and forth, and so on, then you have to converge to the solution quickly. Why is this the case? So imagine a sequence of minds. This is the mind that triggered first. This is the mind that got triggered by its explosion. Then you went to some other mind. Then this one triggered the mind over here. This one triggered the mind over there. And then this one triggered another mind somewhere on this side. Now, if we are going through the minds from the left to the right, then we will process all of these things in a single pass. So when we look at the range of this mind, we will discover this one and extend the range of this. And then, it's the opposite way. So if we are going through the minds in this direction, then we'll do this entire branch in a single pass. Because first we will process this mind, and we'll process nothing new. Then you will process this mind and learn about this one. And then you will process this mind and learn about this one. And already for this one, you knew that this one will be exploded. So for this one, you update it also with the information from that. So if you go through the minds like this, you will solve this entire thing. You will learn this entire thing at once. And then if you go through the minds like this, you will learn this entire thing at once. So the question now becomes, if you want to go from one mind to another through a series of explosions, so you want to do something like this, that each of the minds has to trigger the next mind in the direction of the arrow. And you want to do this in the smallest possible number of changes of direction. How large can this number of changes of direction be? So you only want to change the direction when you are forced to do so. And the question is, what is the maximum number of such occurrences? And the answer is that it has to be very small, because each change of direction has an impact on the ranges of those minds. In particular, if you can get from here to here by going through the other side, but not directly, this means that the range of this mind must not be sufficient to reach this one, but the range of this mind, which is farther left, already has to be sufficient to go all the way back and then even farther. So what happens here is you can show that something along the lines that whenever you are forced to change directions twice in a row, then the length of your range will at least double. Because again, like if I wanted to go back again, I have to go even farther than the range of this one. And farther in the range of this one is definitely more than double of the range of this. So whenever I went here to the left, I had to find in some range. And if it pays off to go to the left the next time, the range of this one must be significantly larger. And now we are getting to a tricky point. All of the numbers in the problem statements are integers that are bounded from above. The maximum value of a range is a 60-bit integer. And this tells us that about, after a constant number of iterations, or about logarithm of the precision iterations, the process has to converge, because we will not have any more mines with an even larger ranges. For any two mines in our input, there has to be a sequence of exploding mines that is going to the right and to the left and changes directions at most roughly 60 times, maybe 120, not more than that. So you just need a constant number of iterations. Well, it's constant kind of. It depends on the size of the input numbers. But as long as they are bounded from above by constant, then you know that there is a very small number of iterations you need. And in practice, the process will converge even faster. So if you actually implement it in the way that after each iteration you have a boolean checking whether something changed, then it will be very fast. And that's it for this last problem of yesterday. Yep. Any questions? So right now we have a quarter to 12. So we have something like 15 minutes left until the supposed end of this session. And in order not to waste time, let's try to have an improvised Q&A session. So should you have any questions related to competitive programming, or possibly not even that, feel free to ask. Is there anything covered in previous days you would like to hear in more detail, or some more questions maybe about contest strategy? Nobody?
I'd like to hear more about the Conway's Army combinatorial argument. Why you can use X and powers of X?
You can, in the Conway's Army problem, let's recall what was happening there, is that we were assigning a numerical value to each cell, based on its Manhattan distance from the desired goal. And essentially, you can do this with completely any numbers. But our goal was to introduce a constraint on the solution. And this may be easier if I show you the second problem I mentioned as an exercise. And the problem will look as follows. So we started with a single token on the upper left corner of an infinite chessboard that looks like this. And the only allowed move was to take a configuration that looks like this and change it to a configuration that looks like this. So you can take a pebble and you can replace it by two other pebbles, but you have to place them on empty cells. So in order to start playing this game, in the first move you have to do this. In the second move you can, for example, change this pebble to this two. And now you cannot make a move here because you don't have an empty cell, but you can move this one to this, and then you can move this one to here and there. And let's do a few more moves, like this, and now you can get rid of that one. Oh, suddenly we have an empty space here, and let's try shifting this some more. One more. Oh, we still have a lot of here. And now we could shift these somehow and try to get rid of that one as well. And the question is whether you can free as many diagonals from the corner as you wish. or whether this process has to get stuck at some point. And the thing you do when you analyze a problem like this one is you will try to assign some numerical values to all of those species you are using in such a way that you can argue about requiring to have many species or requiring to have that you have not enough room for those species you would like to have. So if you actually try playing this game a little bit more, you will see that you will need more and more steps just to free a single cell somewhere here. And it seems like you are getting stuck. It seems like there is not enough room for all of those new pebbles you would like to put there in order to be able to move this one even one step farther away. And now we want to formalize this feeling. We want to formalize this notion that there isn't enough room. So what you is you assign some numerical value to each of those cells, and you try to compute exactly what is going on. And in this case, it's quite clear what's happening here, that you take one pebble on one diagonal, and you replace it by two pebbles on the next diagonal. So a quite natural guess of these numerical values would be that the value of this one is the same as the value of those two. And we can do this by simply using powers of 2. So a pebble here is worth 1. A pebble here is worth 1/2. This diagonal is 1 divided by 4, 1 divided by 8, 1 divided by 16, and so on. The good property of this choice is that at any moment in the game, the sum of the pebbles is exactly 1. You started with 1, and whenever you divide a pebble into 2 new ones, the new ones each have the value that is the half of the original one. So each valid configuration, each configuration you can reach, has to have this property. This is the invariant you wanted to see. Whatever configuration you are able to reach, the sum of the pebbles, sum of the covered cells, will be exactly 1. And now we can start some kind of computation. So let's say, let's take this piece of the board, and let's ask the question, is there a finite sequence of moves that will clear this completely? So is there a finite sequence of moves such that all of the pebbles are in this part of the infinite board? And in order to answer this question, you can find a very easy necessary condition. It's not obviously whether it is sufficient, but it is necessary. And the necessary condition is the sum of all of these cells, infinitely many cells, has to be greater or equal than 1. Because as soon as it turns out to be the case that the sum is less than 1, then it means that even if you cover the entire plane with pebbles, except for this corner, you will still not have a valid configuration because the sum of those pebbles will not be equal to 1. So, for a solution to exist, you must have this. And now you can take the actual values, and you can sum and check whether you have this. So in this first row, we have starting from 1/16, and so on. In the second row, the third row, the fifth row, and so on. So in each of these rows, we are starting with 1/16. We are going on and increasing it. So this is 5 times plus. In this row, we are already starting from 1/32, and so on. In the next row, we are starting from 1/64. And now each of these things in the parentheses is a simple geometric sequence. So we can easily compute what's the result. And in this case, this is 1/8, right? This is 1/16, and so on, because like if you have 1, this is 1/2, and this is 1/4, and this is 1/8, and so on. And if you take the infinite sum from some point, you will get the entire square. So 1/2 plus 1/4 plus 1/16, and so on is 1, and this is the same in scale. So this entire sum is 5 times 1/8 plus 1/16 plus 1/32 plus until infinity. And again, this is another 1/8, so this is just 6/8. So this tells you that the sum of this entire part of the plane is less than 1, and therefore you need to have at least something here. In fact, you need to have at least 3 of them here, because you need to be strict. You have this part has to be strict less than 1, so you know that you will have either a pebble here and here, or at least 3 pebbles in this diagonal. And the same thing goes for Conrad's army, where the argument is slightly more complicated, because in this case, each move exactly preserves the sum. And in Conrad's army, the constants are chosen in such a way that each good move preserves the sum, but there are also some bad moves that decrease the sum, but this doesn't help. So still the game is the same. In order to reach this particular cell, you need to end with a configuration that has a sum of 1. And we chose the value of x in such a way that we have this property. You can never increase the sum of your configuration. And then we can compute that for this particular x, any initial configuration will have a sum less than 1. And this is the full proof why it is impossible. And this is a very nice area in general in discrete mathematics, this topic of various invariants. Like the most standard one, obviously, is the chessboard pattern. So if you have the quintessential problem on this is you have an 8-by-8 chessboard. Now you cut off 2 opposite corners, and the question is whether or not you can cover the entire chessboard by dominoes that have size 2 by 1. The first check, the first invariant will be the area. The area is 62, which is even, so this seems okay. But then obviously what you can do is if you draw the chessboard pattern, black and white cells, then you see that the original chessboard had 32 white and 32 black cells. You see that each of the dominoes has to cover a white cell and a black cell, but unluckily both the opposite corners were of the same color. So right now we have a situation where we have 30 cells of this color and 32 cells of the opposite color. So whatever you do, you can place at most 30 dominoes, and then you will be left with 2 cells of the same color that cannot be covered. So this is the easiest invariants you can have, the parity and the chessboard pattern. But there are also some problems that are more difficult to solve, and looking for these patterns, looking for these invariants can be very rewarding. Let me give you a few tasks to think about. And the first task to think about, you have a 10 by 10 square, and you have pieces that have size 1 by 4. And the question is whether you can tile the entire 10 by 10 square using copies of such pieces. They can be rotated by 90 degrees, but they cannot overlap, they cannot stick out of the square. So an initial check would be that the area is 100, divided by 4 is 25. It seems plausible, should be possible to put them inside somehow. And also if we do a check with the white and black cells, we will see that everything seems to fit. There is 50 black and 50 white, and each of these will cover 2 black and 2 white. So still everything seems in order. So maybe it goes, maybe it doesn't. We'll try, we'll see. Another problem to think about, you have a 9 times 12 rectangle, and the pieces you can use are the L's from Tetris. And again, you are allowed to use, you are allowed to use all kinds of rotations and reflections. So there are 8 different placements of an L. And the question remains the same. is it possible to tile the entire rectangle using these pieces? These are two of the not completely trivial questions, and in many cases there are very easy arguments once you see the correct invariant, but discovering it can be hard, and this can be also one of the hard and very rewarding problem-solving areas. Another traditional problem from this area, you may have heard of the 8 queens problem, or maybe n queens problem. You have a chessboard, and you want to place as many queens as is the dimension of the chessboard, so that no two of the queens attack each other. This can be solved on an on a standard 8x8 board. There are some placements of queens that don't attack each other. So try solving the same question, but on a torus. So instead of having just a chessboard, there is a square, and the diagonal lines end at the boundary. Imagine that to the left of the leftmost column, you have again the rightmost column, and also the board continues like this. So you have the standard chessboard. And you have a queen here, and you can travel a single move like this. So this is obviously more restricting because any configuration of queens that do not attack each other on a torus is also valid for the official solution, official version, but with just regular chessboard. And the question here is whether it is possible to find a valid solution for n equals 8 on a torus, or maybe if you are feeling for a harder problem, for which larger n there is a valid solution on a torus. And again, this is a problem, well, certainly for n equals 8, this is a problem that can be solved by brute force. We'll just write a vector key solution or a solution that tries all permutations and check whether there is a solution. But there is also a pen and paper argument for the torus version of the 8x8 problem that is reasonably short. So you may try thinking about it and trying to discover it. Well, obviously for n equals 8, if there is an argument, it means that there is no solution. So we are looking for a proof that there is no solution for 8 queens on a torus. And again, there is some kind of an invariant that can be used there. The queens have to satisfy something, and you don't have enough of it. So if you are into these combinatorial problems, then especially these two should be a nice exercise to think about. All right, and I think we are, yeah?
The C World Finals next year, there will be some teams solving problems using heuristics.
Using what?
Then maybe the solution would not be using heuristics, but some teams maybe will be using heuristics. How to decimate this problem, this issue of the problem it is you to solve using so exact algorithm, but solutions with heuristics may be accepted.
There's a kind of two sides to this coin. In programming contests, there are some problems that have the property that you can easily guess the solution. And if you do encounter such a problem in a contest, then by all means, I encourage you to guess the solution and to submit it. So if you examine the small inputs, you see a clear pattern. For instance, the correct answer is yes, only if n gives the remainder 3 modulo 8 or something like this. If you see for the first 1,000 cases, then by all means submit a full solution and see whether it gets accepted. At the same time, as a problem setter, I'm sometimes hesitant to use such problems. I will use such problems maybe from time to time, but I will try to push them towards rounds where it doesn't matter as much. For instance, if this would be Google Code Jam, I would expect such problem in round 1, but I would not expect such a problem in the finals, because the problem setters, I think, feel the same about this as I do. And the idea is not to reward this guesswork by as much. It is a valid problem-solving strategy, but it doesn't feel complete. Like, the preferred way of solving problems we would have is that at the moment when we are submitting the solution, you also have an idea why is it correct. You could be able to do a proof if you had to, and such. So already problems like this one are problems I wouldn't expect to see at the ICPC World Finals. There may be one such problem per problem set. If there are more, I will consider the problem set bad, and I will consider the fail of the judges that they posted such a problem set where many of the correct solutions could have been guessed without having a proof. Of course, this is something where it is very hard to draw a line, because sometimes, quite often, the guess will be an informed guess. You are guessing the pattern of the solution based on your past experience with problems. You are guessing the pattern of the solution based on your intuition. Sorry, for example, there have been problems, I think in MaratonIME there has been a problem where you have to find a click in the graph or something along those lines. I don't remember the problem completely, but a part of the solution was to realize that the answer can be at most 6, and then you could try all possibilities of solutions of the size 5, and if none of them work, you got to 6. Something along these lines. And there is a mathematical proof behind this property, but you could also argue some bound like this intuitively. And there is a gray area whether this is a correct approach or not. You have an intuition based on your past experience. You have seen problems like this one, you know how it behaves. You made a guess, and you made a submission based on the guess, and it turned out to be correct. So this is something for the problem setters to decide, and sometimes you discard such a problem, sometimes you use it based on the personal preference, based on the amount of other problems you have available. Sometimes this is the lesser of two evils. And then there is another category of problems. And these are problems for which there are incorrect heuristic solutions. But there can be some classes of problems, some types of problems, for which it is really, really hard to design good test data. So, for example, it can be the case that you can write a solution that is incorrect, but only fails very infrequently. And if you start a solution by randomly permutating an input, then you are very likely not to hit such cases. And there can be other cases where simply the number of different heuristics is so large that it is hard to think about all of them and prepare test data that is good against all of them. And there have been cases, for instance, at the IOI, when a problem has been discarded because it was a nice algorithmic problem, but it was too hard to design good test data for the problem. We were not able to guarantee that there won't be incorrect solution to pass. And as we found it very likely that there would be such attempts, that the contestants would spend 50 attempts on tweaking an incorrect heuristic solution until they get it to pass. We simply discarded the problem and said that this is something we are not able to use. The underlying algorithmic problem is very pretty. It will be a beautiful theoretical task, so we will have to write down the solution on paper, as in the IMO. It will be an excellent task, but we simply cannot use it in this black box testing environment. We cannot prepare to test the cases. And again, this is very hard to judge. This is something for which you need experienced problem setters, people who have already encountered such situations and know how to recognize them. Again, it comes down to empathy, it comes down to intuition that, oh, this may cause problems, I'm afraid of this, let's not use it. And it's hard, so again, it may be the case in the future, the World Finals of ICPC, that we will see such a problem here and there, because it went through under the radar and nobody called it until the actual contest. It may happen. I wouldn't expect it frequently, because many of the also World Finals judges are very competent people who know what they are doing, who have loads of experience. It may happen, but it's not something I would expect regularly, and definitely is not something I would spend time practicing for. If you do get into such a situation, you should recognize it anyway. If you see that everybody is getting it accepted and you have a wild guess, go ahead, submit it, and that's the best you can do in such situations. Alright, so I think we exhausted the topic, we exhausted the audience, so let's go ahead and